In this lecture, we'll be talking about one of the most important items about matrices, okay? It's the concept of invertible matrices, okay? So, as we said before, that In, the identity matrix of size n plays the role of the number 1 for multiplication of matrices. Similar rule that one plays between multiplication of numbers, In plays it between the product or multiplication of matrices, okay? So how do we define the inverse? Okay, how do we define the inverse? So first of all, let's go back to the real numbers. So what do we have? We have 1 over a, which can be written as a to the power 1. But what does define this number? This number is defined as the number such that, of course, a cannot be equal to 0, such that a times 1 over a gives me 1, that famous unit. So we can write this as a times a inverse equals to 1, right? Great. And of course, we do have, obviously, that equals to 1, because the multiplication between numbers is commutative. Okay, so we don't have a problem, we don't have an issue. And this will allow us to, for example, this will allow us to define the division of numbers by writing b over a being simply b times a inverse. That's how we defined the division. Okay, so once you have the inverse of an element, then the division comes natural as well. Okay, so we are gonna mimic this into matrices now. Okay, into matrices. So how do we want to do it? We take A, and we are looking for A inverse. So here, A inverse. That's what we want. And what do we want? We want A times A inverse to be equal to A inverse times A to be equal to I. Okay? For this reason, A has to be a square matrix, and A inverse will have the same size. Okay, so basically A is a square matrix of size n. So A inverse will be a square matrix of size n, okay, and we have, so now we can be a little bit more precise, A times A inverse equal A inverse times A equals In. Okay, so it's the identity matrix of size n. Okay, so basically this will be our definition. Okay, meaning that A is invertible or has an inverse, okay, if and only if there exists a matrix same size B such that AB equals BA equals IN. Okay. First, note that you cannot have two inverses. If you have one, it's unique. Why? Because if AB equals BA equals IN and AC equals CA equal IN, then B is equal to C. Okay? So one way to see it is to compute C, indeed. C times A times B is going to be C times I, which is C. On the other hand, it is also equal to C times A times B, and C times A is I times B, B, and therefore B is equal to C. Okay, so if we have an inverse, it's unique. So this, if we have an inverse, if we have an inverse, it is unique. Okay, now why do I say if we have an inverse? Okay, so first of all, let us look at the general common sense. Okay, so we would like, since we inspired ourselves from the real numbers, to have something similar, meaning what? That if A is not a zero matrix, then maybe A inverse exists. Okay, so we are mimicking what happened on the real numbers. Okay, okay, let's find out. Take A to be 1, 0, 0, 0. Okay, so A is not equal to 0. Okay, so A is not equal to 0. Set B equal 0, 0, 1, 0. Then A times B, simple exercise of multiplications. Let's put here 0, 1 for the sake of. Then it's simple, okay? Simple calculations will give me 0, 0, 0. Okay? Okay, now assume A inverse exists. Okay, assume, because A is not equal to 0, so maybe we have an inverse, like the real numbers. Okay, so in this case, let's look at A inverse times AB. What's this? So this is A inverse times the zero matrix, which is 0. Anything multiplies zero matrix gives you 0. Okay, and now we use the properties of the multiplication, basically the associativity. We get A inverse times A times B. And what is A inverse times A? That's I times B, and that's B. So in other words, we find that B is equal to what? To the zero matrix. But we know that's not true. This is not true, because B is not equal to 0. Therefore, A fails to have an inverse. So the rule that non-zero matrices, they have an inverse, is not valid anymore. Okay, so it's a little bit more complicated. It gets more complicated than the real numbers. Okay? Okay, so now we have an interesting result. So before we go to that result, let me take another example. So we touched on it in the previous lecture, and we called it the Cayley-Hamilton result. Okay, so now instead of giving you a numerical example, let's take any A which is a 2 by 2 matrix. Okay? And let us take P of X. It's very similar to what I was doing in the previous lecture on the algebraic properties of matrices. But let us take x squared minus a plus d times x. And by the way, a plus d is the trace of the matrix A, plus ad minus bc here, which is the determinant of A. And let's look at P of A, which is a squared minus a plus d times A plus ad minus bc times a to the power 0, which is I2. Okay? So here is a pure algebraic calculation, and I leave it to you to do it, and you will find that in fact P of A is equal to the 0 matrix. So in other words, very interesting. Okay? So now let us take the identity matrix to the other side. So what do we have? We did exactly similar in the previous lecture, okay? A squared a plus d times A equal ad minus bc times I2. Now let us factor out A. And let us put A minus a plus d times I equal ad minus bc times I2. So now what happened? Okay, we want to divide by this number ad minus bc. So assume ad minus bc not equal to 0. Okay, so in this case we set b to be 1 over that number, the determinant, times a minus a plus d times I2. And what do we have? We have a times b equals I2. And since b is just a combination of a, which commutes with a, and I2, which commutes with a, we do have also b times a equal to a times b equals to I2. In other words, that a is invertible. Okay? Okay, if the determinant, if AD minus BC is equal to 0, then we have A times A minus A plus D I2 is equal to what? 0 times the identity matrix is the 0 matrix. Okay? In other words, what we found a matrix A times B gives me what? The 0 matrix. Okay? Which means what? That A inverse will never exist. Will not. We discussed this. Will not exist. Okay? For the same reason as we said before, huh? For the same reason, for the example, of course, huh? Same reason, okay? Therefore, A, in our case here, in our 2 by 2 matrix, we found what? That A is invertible if and only if AD minus BC not equal to 0. So it shows you the complication, okay? For a real number, a number has an inverse if and only if that number is not equal to 0. For a matrix 2 by 2, look how complicated it is. You have an inverse if and only if this quantity here is not the matrix itself. Okay, it's this quantity AD minus BC not equal to 0, which is the determinant. So it shows how complicated it is. It is quite complicated in the case of. So what did we found? We found that in this case, A inverse was 1 over AD minus BC times A minus A plus D times I2. And we can do the calculation, and we will find that A inverse equal 1 over AD minus BC. Let me. there was a mistake. Oh, sorry. I did a mistake. Here, the mistake is right here. So it is a minus because it was a plus here. And therefore it is a minus here, and therefore it is a minus here. It is a minus. It is a minus. Okay, so then we have what? We have A, B, C, D minus A plus D, the trace, times 1, 1, 0, 0. So this will give me minus 1 over AD minus BC time A minus A0 minus D, B minus 0, C minus 0, and then D minus D is gone, minus A. And if I remove the minus, I will find AD minus BC, the determinant, time D minus C minus B, A. Okay? So the elements on the diagonal, they changed, they interchanged, A and D. The B's and the C's are the same position, but they are with a minus. Okay? So this is an example of what the inverse look like in the case of 2 by 2. It shows you the 2 by 2, we can handle all these calculations, and it shows you what happened when you go to 3 by 3, 4 by 4, etc., etc. It gets awfully complicated now. Okay? So, application to systems. So let us consider the system AX plus BY equal E1 and CX plus DY equals E2. So we can write the system in terms of matrices. The matrix representation will be A, B, C, D times XY equal E1, E2. Okay? And what's amazing is what happened if AD minus BC not equal to 0. Okay? Then the coefficient matrix, is invertible. Okay? And in this case, what we have XY is equal to the inverse times E1, E2. Okay? Because we can multiply and you will find that. So what does that mean? It means that the system has one solution. In fact, this, as you can see, this conclusion has nothing to do with 2 by 2. It can be any system with n unknowns, with n rows, and the coefficient matrix is invertible. The system has only what? One solution. Okay? If the coefficient matrix is invertible, we have only one solution, which is the inverse of the coefficient matrix times the non-homogeneous what? Column vector. And in this case, because we know, this will lead us to what's known as Cramer's formulas, because we know what are what's the inverse is just AD minus BC time DA minus C minus B times E1, E2. Okay? So this tells you X is equal to D E1, B E2 over AD minus BC, and Y is equal to A E2, C E1 over AD minus BC. Okay, do we have something for 3 by 3, 4 by 4, etc., etc.? The answer is yes, and we'll see them later on. before I close this window, let us look at the relationship between the inverse and the transpose operation. So here it's easy to see that if A is invertible, okay, then we know that A times A inverse will be equal to In. Okay, so let us take the transpose. So we get A inverse transpose equals In transpose, which is In. So the transpose of the identity is just the identity. And now we use the beautiful property of the transpose of a product. So this will be transpose time A transpose equal In. And if you use now A inverse time A, you will get also A transpose time A inverse transpose. So you found a matrix B, which is A inverse transpose, such that it multiplies A transpose from both sides, gives you In. Therefore, A transpose is invertible. And not only that, we even have the inverse. A transpose inverse. What is the inverse of the A transpose? That's the transpose of the inverse. So in particular example, if A, just for the sake of A, B, C, D, okay, and AD minus BC not equal to 0, then we know that A transpose, which is A, B, C, and D, okay, is also invertible, because we're going to have AD minus BC not equal to 0. So that number is the same. And A transpose inverse is going to be the transpose of A inverse. And we know that the transpose of A inverse will be, I mean, we can use the formula, but we can also say this is 1 over AD minus BC time DA minus C minus B. That's the formula we found, transpose. And this will give me 1 over AD minus BC. D stays, the diagonal, and we just change the element, we reflect that. So we find that the formula is, we could have used the formula, general formula, to find it, but it's valid, okay? Still it works here. We can just check it, in other words, okay?